Welcome to Ordinary Differential Equations, Lesson 31. How to solve a differential equation like this. If we look at this, we will notice that it is a second order differential equation because we have a second derivative here, first derivative here. Instead of constant coefficients, we have functions, a of x, b of x, and c of x. And we want to solve the homogeneous equation that a of x times the second derivative of y plus b of x times the first derivative of y with respect to x plus c of x times y equals 0. And the methods that we discussed before don't hold in this case because this is not constant coefficient. So we're going to introduce the Frobenius method for solving this. Along the way, we'll have to talk about singularities of differential equations. Let's talk about singularities of functions. A singularity is a place, in this case a value of x, where the function is not differentiable. Let's look at a couple of examples. Suppose we have f of x equals 2x divided by x plus 1 squared minus 5 over x minus 2 cubed. If we look at this first term, for instance, when x equals minus 1, this denominator is going to be 0. And so 2x over x plus 1 is going to be a very large magnitude negative number close to x being minus 1. And so as we approach x equals minus 1, either from the left or from the right, the function goes downwards. The graph of the function drops down. That's because the limits, in this case the one-sided limits, in both cases are going to be minus infinity. The limit of f of x as x approaches minus 1, either from the left or right, is minus infinity. So that tells us that we have a singularity, f has a singularity at minus 1. Also, we have a singularity at x equals 2 for a similar reason. As x gets closer and closer to 2, this denominator gets closer and closer to 0. X minus 2 cubed gets closer and closer to 0, but the numerator remains at 5. So in that case, as x approaches 2 from the left, the function goes off to plus infinity. As you approach x equals 2 from the right, the limit of this function as you approach x equals 2 from the right is minus infinity. And so we have singularities at x equals minus 1 and at x equals 2. There's nothing we can do about rectifying this situation. However, here's a situation in which we can easily change the function just slightly to make it differentiable. Suppose we look at the function g of x is defined by x cubed minus 8 divided by x minus 2. If you do this division, you notice that x cubed minus 8 has a factor of x minus 2 in it. So you can divide this out and get a polynomial. But g of 2 is actually not defined because when you plug in 2 into this formula, you'll just get 8 minus 8 over 2 minus 2. In other words, 0 over 0. And so g of 2 is undefined. But if you look at the limit as x approaches 2 of g of x, it equals 12. As we get closer and closer to x equals 2 from the left, or as we approach x equals 2 from the right, the values of this function get closer and closer to 12. There's one point missing on this graph. This graph is a parabola, except it's missing this point, which is 2, 12. So if we redefine g just slightly, say that g of x is equal to this formula for x not equal to 2, but let g of 2 equal 12, then we can remove that singularity and have a nice differentiable function everywhere, including at x equals 2. Our first goal is to solve the differential equation second derivative of y with respect to x plus p of x over x dy dx plus q of x over x squared y equals 0. We're going to put conditions on p of x and q of x, so we're just going to look at a certain set of these types of differential equations. We will consider the case where p of x and q of x in that differential equation have power series representations centered at x equals 0. If we have our differential equation in this form, we can rewrite it in this form. Notice all we did was say that p of x over x times y prime is equal to p of x times y prime divided by x, and similarly this term can be rewritten this way. We're going to look primarily at this form of the differential equation. We'll assume that p of x and q of x have power series expansions about 0, and we will attempt to find solutions of the form y equals x to some number r times the power series, the sum k equals 0 to infinity, c sub k, x to the k. Notice that this is a power series of x centered at 0, and before we talked about power series centered at other numbers like a, where we would have x minus a to the k here, and maybe in that case x minus a to the r here also. But we're going to start with looking at a simple example with power series expansion about 0. The main idea of the Frobenius method is to look for a solution to the ordinary differential equation, which we will write in this form. And we're looking for a solution of the form y equals x raised to some power r times this power series. The sum k goes from 0 to infinity, c sub k x to the k, which we can also write this way by bringing that factor x to the r inside using the distributive property. So y of x we can think of as x to the r times this power series, or if we look at it this way, we can think of it as c naught x to the r plus c1 x to the r plus 1, and so forth. Notice that the power series portion, this portion right here, is a power series centered at 0. You can use the Frobenius method for other centerings also. If we want to look for a Frobenius solution centered at some number a, we could let y equal x minus a to the r times the sum k goes from 0 to infinity, c sub k times x minus a raised to the k power. In this lesson, the problem we will consider we'll have x equals 0 as a singular point of the ordinary differential equation. But if we use a Frobenius series centered at 0, we can still get a power series solution that holds on both sides of x equals 0. So this has an advantage in that we get a longer interval of convergence for this power series in many cases than we would if we just looked at an ordinary point, which we'll talk about later too. In the expansion, y equals x to the r times this infinite series, r represents a real number, and there are some values of r for which this thing will be a solution to the ordinary differential equation, and other values of r, well, this will not be a solution to the differential equation, no matter what values of the c sub k's you pick. So one of the things we'll have to do is find the values of r that allow us to continue, because there may exist a solution of this form for that particular value of r. We're looking only at second order linear differential equations, homogeneous also. So we know that a solution space is going to be two-dimensional. There are going to be two linearly independent solutions to our ordinary differential equation. Sometimes we can find one solution of this form and use some other methods to find the second solution. Or it could be that we can find two solutions of this form for two different values of r. We can require C0, the first coefficient in this power series, this part right here. We can require C0 to not be 0. For example, suppose we had x to the minus 1/2 times this series, 0 plus 2x minus 1/5 x squared, and so forth. What we can do is say, well, if I multiply this out, what I have is 2x to the 1/2 power minus 1/5 x to the 3/2 power, and so forth. And that can be also written as x to the 1/2 times 2 minus 1/5 x plus, and so forth. So if we write it this way, the C0 value, the first coefficient of the x to the 0 term right here, is non-zero. So if we have something like this, we can basically fidget with the factors that we have in front so that we start with a non-zero constant right here. At this stage, it's not obvious that we should look for a solution of this form, x to the r times the power series. But we will find that we do get at least one solution of this form to that type of differential equation under circumstances that we'll discuss, and maybe, perhaps, even two linearly independent solutions of this form. We will see this as time goes on, so don't worry at this stage if it seems a little bit mysterious. So let's look at this differential equation, and let's look at what happens if we substitute into this differential equation y equals x to the r times this power series, which we can write also as the sum k goes from 0 to infinity c sub k x to the r plus k. And let's start with this y over x squared here. If y equals this, then y over x squared is going to equal the sum of c sub k x to the r plus k minus 2. If we divide r plus k by x squared, that's going to be x to the r plus k minus 2. Since we had a sum going from k equals 0 to infinity here, this one also will be 0 to infinity. Now, let's look at y prime over x that we have right here. Y prime, if we just differentiate y up here, y prime is the sum, k goes from 0 to infinity, c sub k times r plus k times x to the r plus k minus 1. What we did was we differentiated this series term by term. The derivative of r plus k is r plus k. The derivative of x to the r plus k is r plus k times x to the r plus k minus 1. Now, if we take y prime, which is this stuff, and divide it by x, that's going to give us something that looks very much like this, except this exponent of x will be x to the r plus k minus 2. Now, if we start with y equaling this thing, and we differentiate it twice with respect to x, we get the sum k equals 0 to infinity c sub k times the factor r plus k times the factor r plus k minus 1 times x to the r plus k minus 2. So what we notice here is something interesting and actually useful. We looked at y over x squared, and it was this sum where x had the power r plus k minus 2. When we looked at y prime over x, it was this series, and it also has terms with x to the r plus k minus 2. And y double prime also can be written as this series with this exponent of x equaling r plus k minus 2. So we have the same power of x in all of these things, the y over x squared, the y over x, and the y double prime. So looking at this differential equation, we saw that y double prime could be written this way, y prime over x could be written this way, y over x squared could be written this way. P of x, remember, is going to have a power series expansion about 0. I should have said that before, I guess. So P of x we're going to assume is P naught plus P sub 1x plus P sub 2x squared plus and so forth. So P of x does have an infinite series representation that converges to P of x. Similarly, we'll assume that Q of x can be written in terms of a power series with constants q naught, q sub 1, q sub 2, q sub 3, and so forth. So I guess one of the first things we should do is, if we're looking for a solution of this form, which has that factor of x to the r in it, how can we start by finding the possible values of r that could possibly give us solutions to this differential equation? So let's see what we can do to find r. Y double prime we saw was this infinite series, and that's equal to this term. This is the k equals 0 term. R times r minus 1 times c naught times x to the r minus 2. If I look at y prime over x, that had this series expansion, and the first term of this series is r c naught x to the r minus 2 plus some other stuff. And when we look at y over x squared, that's this series right here, and that's going to be c naught x to the r minus 2 plus some other stuff, where c naught is not equal to 0. So now let's look at the sum of the x to the r minus 2 terms. This first one, from this first term, all we get is r times r minus 1 c naught x to the r minus 2, and that's right here, r times r minus 1 times c naught times x to the r minus 2. Okay, looking at this term in the differential equation, when we multiply p of x times this, we're going to multiply p naught plus some more terms times this stuff, r c naught x to the r minus 2 plus some more terms. When you multiply those two together, you're just going to get P naught times R times C naught x to the R minus 2. When we look at this term over here, Q of x is Q naught plus some higher order terms, and y over x squared is C naught times x to the R minus 2 plus some higher order terms. And so when you multiply this times this, what you get is Q naught C naught x to the R minus 2. So the sum of the x to the R minus 2 terms that we got from this, and this is just this stuff here. Now we want the power series representing this to equal the power series representing the zero function, which means that every term in the power series expansion of this side has to be 0. So in particular, the coefficient of x to the R minus 2 has to be 0. Well, C naught was not 0. Remember, that was one of the things that we specified up here. And so that means that this other factor right here has to be 0. R times R minus 1 plus P naught R plus Q naught equals 0. This is a quadratic equation that R must satisfy in order to have a fighting chance to find a solution to that differential equation. This equation, quadratic in this case, is called the indicial equation for the ordinary differential equation. And we're going to solve it for R when we try to find this power series representation of the solution to this differential equation. So we want to solve the ordinary differential equation that we have up here. So first we solve the indicial equation for R, and we saw that equation is R times R minus 1 plus P naught R plus Q naught equals 0. The P naught and the Q naught came from the power series representations of the functions P of x and Q of x. So then we find the power series for this expression, y double prime plus P of x, y prime over x plus Q of x times y over x squared. This must represent the zero function. And so what we'll do is, once we write out all of these things in terms of series, we'll combine like powers of x. Then, since this stuff equals a zero function, that must mean that each distinct power of x term must have a coefficient of 0. So that gives us a bunch of equations to solve. So in fact, it's going to give us a recurrence relation. So solve the recurrence relations to find C sub 1, C sub 2, C sub 3, and so on. C sub naught can be picked to be arbitrary and still get a solution to this differential equation. If we have an initial value problem, however, we might have to determine what C naught is in that case. So now let's look at this example. Let's solve x squared times the second derivative of y with respect to x minus x times the derivative of y with respect to x plus the quantity x squared plus 8/9 times y equals 0. The first thing we'll do in our solution is to divide each of these terms on each side of the equation by x squared. And so when we do that, what we have is the second derivative of y minus y prime over x. And where did that come from? If we divide this by x squared, we'll have x over x squared here, which is going to be 1 over x. 1 over x times y prime is what we have here. Okay, and then this one over here, we can do something similar, I guess. we will divide this by x squared. I put it right down here, division by x squared. And on the right side, 0 divided by x squared is 0. Okay, so now what we'll do is start plugging in what these things are that we saw before. Y double prime is this series right here, minus y prime of x. Y prime of x is this series right here, plus x squared plus 9 times y over x squared. That's right here, x squared plus 8/9 times, and here's the series for y over x squared, and this equals 0. Okay, now going from this line, which was just pure plug-in for these things right here, down to this line here, we're just going to change one thing. This term, this series, is the same as this series. This series right here is the same as this series. And now we have x squared plus 8/9 times this. Well, we can write that as x squared times this series plus 8/9 times this series. And so that's what we have here. X squared times that series plus 8/9 times that series. On the right-hand side, we still have 0. Okay, on the next line, only one thing changed. We have x squared times the sum of this stuff raised times x to the r plus k minus 2. If we multiply x squared times x to the r plus k minus 2, that just becomes x to the r plus k. This term over here, this infinite series, is the same as what we have here. So now let's go down to this last line. This series is the same as this one. This series is the same as this one. This series is just a re-indexing of this one. Instead of going from k equals 0 to infinity, we went from k equals 2 to infinity, and we replaced all of the k's here with k minus 2's. And then this series here is the same as this series here. Okay, so we're making some progress. If you look at what we have on this last line, we're still in pretty good shape. X to the r plus k minus 2 occurs here. X to the r plus k minus 2 appears here. X to the r plus k minus 2 appears here, and also here. The same exponent of x in each of these infinite series representations. So let's see, where are we? We're solving this differential equation. We plugged in the infinite series for y into each of these terms, and we came up with all of this. We noticed that all the powers of x were r plus k minus 2's. There's one slight fly in the ointment. Where does the summation start? Here it's 0 to infinity, 0 to infinity, 2 to infinity, and 0 to infinity. It would be nice if all of these sums went from k equals 2 to infinity. So what we'll do on each of these summations that go from 0 to infinity, we'll pull out the k equals 0 and k equal 1 terms, put them in front, and then let the rest of the summation start with k equals 2. Okay, so when we look at this first infinite series, when k equals 0, we have r plus 0 times r plus 0 minus 1 times c sub 0 x to the r plus 0 minus 2. That is just r times r minus 1 c naught x to the r minus 2. When we let k equal 1, we will get r plus 1 times r plus 1 minus 1, which is r, times c sub 1 x to the r plus 1 minus 2. And that turns out to be r plus 1 times r c sub 1 times r minus 1. Okay, do the same thing with this next infinite series. The k equals 0 term is r c naught x to the r minus 2. The k equals 1 term here is r plus 1 c1 x to the r minus 1. Move on to this one. It already starts with a 2, so we don't have to do anything with this infinite series. So we'll move on to this one. The k equals 1 term, the k equals 0 term is just going to be 8/9 c sub 0 x to the r minus 2 power. R plus 0 minus 2 is r minus 2. The k equals 1 term here is 8/9 c sub 1 x to the r minus 1. Okay, plus all the rest of the terms from these 4 series, all starting at k equals 2. So now we want to simplify this a little bit further so that we can start setting some things equal to 0. So first of all, let's collect all of the r x to the r minus 2 terms. I have these in red, here, here, and here. And so r times r minus 1 minus r plus 8/9 times c naught x to the r minus 2 is right here. If we gather all the c1 terms together, we have this one, and this one, and those are shown right here. And then, since all of these sums go from k equals 2 to infinity, and they all have the same representation of the power of x here, we can easily combine these together as a sum. K goes from 2 to infinity of this stuff right here times ck, which is right here, minus this stuff right here, which we have right here, plus this stuff, which is just a c sub k minus 2, plus this 8/9 c sub k, which is right here, all multiplied by that common factor of r plus k, x to the r plus k minus 2. And so that equals 0. And this equation has to hold for all x in some domain, probably an interval, where it converges. So that's nice, because if this series, which starts up here and continues down here, has to be 0 for all x in some domain, then this coefficient of x to this power has to be 0. This coefficient of x to this power has to be 0. And all of these coefficients of x to these powers have to be 0. And so that's going to give us some equations that we can solve for C0, C1, C2, and so forth. So here is the equation that we had on the previous slide. This is an infinite series in terms of powers of x. So this term right here, you can do a little bit of algebra on to simplify it. R times r minus 1 is r squared minus r. Subtract another r and add 8/9, and you have r squared minus 2r plus 8/9 times this stuff. Then if we move on to this one, that can be simplified also with just a little bit of algebra to r squared minus 1/9 times c1 x to the r minus 1. Then on this sum that we have here, we have two things in here if you look carefully. We have some c sub k terms and we also have a c sub k minus 2 term here. We have one term of c sub k minus 2. All these other terms involve c sub k. We can do some algebra on that also and write this sum as the sum k equals 2 to infinity of the following stuff. All of them have the same exponent, x to the r plus k minus 2. We have this stuff times c sub k plus that c sub k minus 2, which is right here. So this stuff right here came from this times this plus this, all times c sub k. Okay, so now let's see what we have here. If we look at this first term that involves c naught, we know that c naught is not 0, and so that forces r squared minus 2r plus 8/9 to be 0. And this is the indicial equation for this ordinary differential equation. Now, if you think about it for a few minutes perhaps, you'll realize that this can be factored into r minus 2/3 times r minus 4/3 equals 0. So r can either be 2/3 or 4/3. These are the two solutions to the indicial equation, and these are the only possible values of r that can give us a Frobenius series solution to that differential equation. But we're not through, not by a long shot. We have to find what C1, C2, C3, C4, and so on are. And it's probably going to involve each other in some way. We'll see. So after substituting the infinite series into our differential equation, we got this stuff equals 0. And we saw that looking at the term here involving c naught x to the r minus 2, this was just the indicial equation that gave us r equals 2/3 or 4/3. So then we can go on to the next term, r squared minus 1/9 times c sub 1 times x to the r minus 1. This coefficient of x to the r minus 1, including the c sub 1, this has to be 0. But if you look at this for a minute, we're looking for solutions to the differential equation. So we know that for a solution, r either has to be 2/3 or 4/3. And in both of those cases, r squared minus 1/9 is not equal to 0. So what we have here is, in both cases, a non-zero factor times c1 has to be 0. And that forces c1 to equal 0. Now, this next term here is going to give us our recurrence relation. For each term in this sum, this coefficient of x to the r plus k minus 2, this coefficient right here has to be 0. So that tells us then that r plus k times r plus k minus 2 plus 8/9 times c sub k, which is what we have right here, plus c sub k minus 2, that has to equal 0. Now, we can solve this for c sub k. Subtract c sub k minus 2 from both sides of this equation, and then divide by this factor over here. So c sub k then is equal to minus this fraction, c sub k minus 2 over the denominator r plus k times r plus k minus 2 plus 8/9. This is our recurrence relation. So here's where we are so far. We looked for solutions to the ordinary differential equation of the form y equals this series. This is often called a Frobenius series. we saw that we could possibly find solutions only when r is 2/3 or r equals 4/3. Hopefully we can find two solutions and they'll give us two linearly independent solutions. We saw that in either case C1 had to be 0 and C0, by our assumption right at the beginning of this lesson, was it has to be non-zero. Let's let C0 be 1 for the time being. So for k going from 2 to infinity, we have this recurrence relation. C sub k equals this fraction, C sub k minus 2 divided by r plus k minus 2 plus 8/9. This recurrence relation, notice, depends on r, which is either 2/3 or 4/3. What's probably going to happen is for r equals 2/3, we'll get one recurrence relationship here, and that will give us one solution to our differential equation. And then for r equals 4/3, this recurrence relation will give us a different infinite series, which will be our second linearly independent solution. And as we know, if you have a linear homogeneous second order differential equation of order 2, there should be exactly two linearly independent solutions, and then all solutions, in other words, the general solution, is just a linear combination of those two. So it's beginning to look like we're in good shape. So here, excuse me, we're going to compute the coefficients in the infinite series solution to that differential equation corresponding to r equals 2/3. That was one of the solutions to the indicial equation. So we'll set r equal to 2/3. We'll initialize c to have 0, 1, and 0 in it. These are the values of C0 and C1. And then we'll have a loop to compute more values to put in the list C. For k in range from 2 to 5, so basically k can run from 2 to 4 in this. With the upper limit here 5, you only get to k equals 4. C dot append, and then here we have the recursive formula for C sub k. So for k in range 2 to 5, we're going to append the value of C sub k. So this loop will append C sub 2, C sub 3, and C sub 4 to the list C. We will then show what the list C has in it. So I'll come over here. I will use Shift-Enter to execute this code. And here's what we get. C now has the contents 1, 0, minus 380, 9/30. So the infinite series that's multiplied by x to the r outside is going to be 1 minus 3/8 x squared plus 9 over 320 x cubed. Let's find the other solution corresponding to r equals 4/3. So to make life easy, I will copy the code that we have up here, come down here, I will paste it, Control V, and I'm going to change this r value to 4/3. Now the rest will stay the same, still have the same recursion relation. We don't get the same values for C as we did before, because the recursion relation, besides depending on k, also depends on that value of r, which in this case is 4/3. So let's execute this code, and we get this. So here's what this tells us about the first few terms in that power series. And that power series is going to be multiplied by x to the 4/3 power. The power series is going to be 1 minus 3/16 x squared plus 9 over 896 x to the fourth. Here is a Python program for plotting one of those two solutions. In the main program down here, we're going to first set num_conf equal to 40. That's the number of terms in the partial sum of the infinite series, approximating the solution. In this case, I'll let r equal 2/3. That was one of the two solutions to our indicial equation. I'll let C be the list with 1 and 0 in it, since C0 is 1, C sub 1 is 0. And here is some code that we just saw. For k in this range, append to the list C the next C sub k value, basically. Print C, just to check to make sure things looked okay. And now we're going to have some code to produce a graph of that solution. I'll start with X list being an empty list, Y list also an empty list. I'm going to have the number of points plotted be 50. I'm going to let delta X equal 2 divided by that number of points. So in this case, it's going to be 2 divided by 50. And then for k in the range of number of points, so this is going to go k equals 0 all the way to num points minus 1. I'll compute an x value for a point that I'll plot. I'll append that to X list. I'll compute a y value, the corresponding y value, so x comma y will be plotted. And that y value is defined by a function that we will call f of x, this x value that we had up here. C, that's the list of C values for our sum, partial sum in this case. R is 2/3 right now, and the number of coefficients that are in the series. And then I'll append that y value to y list. After this loop goes through about 50 times, we will plot x list versus y list. Up here is the function that evaluates the partial sum for our infinite series solution at the point x. So I'm going to define a function f of x, c, r, number of coefficients. I'll do a summation right here. Sum equals 0 for n in the range, number of coefficients, sum plus equals c sub n times x raised to the nth power. Plus equals here, if you remember in some programming class like a C or C++ class, or Python class for that matter, this is the same as writing sum equals sum plus this stuff. So after we compute this partial sum by initializing it to 0 and then adding more and more terms to the sum, we will output that value of sum multiplied by x to the r. Remember that we're looking at a Frobenius series, which is x raised to the r power times that infinite series, which in this case is going to be approximated with a partial sum. And then we'll return that output to the main program where it was called right here. So the output will be stored in y, and then we, as we saw before, we append that value of y to y list. So this basically is the program that's going to plot our solution, and in a minute we'll see what the solution looks like. So here's the graph of the solution to the differential equation corresponding to r equals 2/3. Y1 equals x to the r, which is x to the 2/3. And then here we have C0 plus C2 x squared plus c sub 4 x to the fourth plus a lot of other terms. The odd terms were 0. As we can see, the graph starts at 0.5 approximately, increases for a while until we're maybe around 0.8 or something, and then after that it decreases. Notice that over in this region the y values are actually negative because 0 is right here. If we go straight across from 0 to about point right here, I guess, we can see that the crossing point for the x-axis drawn the normal way is maybe around 1.75, not quite. Okay, so let's look at the solution corresponding to r equals 4/3. In this case, y sub 2, our second solution, is x to the 4/3, that's x to the r, times this infinite series, 1 minus 3/16 x squared plus 9 over 896 x to the fourth plus some other even power of x terms further out. And the graph looks about like this. I think earlier when we were looking at Sage Math, I misread this as 9 over 898, but the correct value was 9 over 896. So let's look at those two functions we found. Here's the graph of y1, and here's the graph of y sub 2. If you look at these two graphs, you can see that this graph, for instance, is not a multiple of this one, and vice versa. If you have two non-zero functions, each is not a multiple of the other, those two functions are linearly independent. So in this case, here are two linearly independent solutions to our second order ordinary differential equation. We found two linearly independent solutions to a linear homogeneous ordinary differential equation. So to get the general solution to the differential equation, it's just an arbitrary linear combination of those two solutions that we already found, the two linearly independent solutions to the differential equation. So what we get for the general solution is y equals some arbitrary constant, which I'll call a sub 1, x to the 2/3 times that power series that we have here. Remember that x to the 2/3 times this power series was one of the solutions to the differential equation. The other solution to the differential equation, linearly independent from the first, was y equals x to the 4/3 times this power series. So the general solution is y equals a constant times what we called y1 plus another constant times what we called y sub 2. All solutions to that differential equation are included in this general formula. We can find any solution by picking values of a sub 1 and a sub 2, two arbitrary constants. Remember that this differential equation had a singularity at x equals 0, and if we look at this, this is an expansion about x equals 0, so is this one, but in the Frobenius series we have these powers of x here. In this case they were positive fractions. Sometimes they could be negative integers, for instance. Lots of things are possible. Let's use Euler's method to bolster our confidence in the Frobenius series solution to that second order differential equation. So we'll want to set up an initial value problem. We want it to correspond to the solution y sub 1 of x, the Frobenius solution where we had an x to the 2/3 factor. What initial conditions could we use? The problem that we looked at was just a differential equation without any initial conditions. Well, here's what we can do. We have our Frobenius series solution in front of us, and we can use that to approximate the values of y sub 1 of 0.4 and y sub 1 prime of 0.4, the initial conditions. Then we'll use that differential equation and those two initial conditions, a second order differential equation and two initial conditions, to solve this problem numerically using Euler's method. Euler's method usually is used with first degree equations or a system of first order equations. So what we'll do is change that to an equivalent system of two first order ordinary differential equations equivalent to our second order differential equation, plus we have these initial conditions, and that will give us an initial value problem with a unique solution. We are now in Spider running a Python program, and the program that we see in front of us, hopefully we will recognize this as the program that produced the Frobenius series, one solution to our ordinary differential equation corresponding to r equals 2/3. Let's run this program. So I'm going to come up here and run this file. And here we see the graph of our function y sub 1 of x. And I need some initial values. So I'm going to come back down here. And here's what I'm going to do. This function f up here is still in the memory and we can still execute it, but we're in the version down here where it was called, and so I'm going to copy f of xcr num coefficients, Control C. I'm going to come over here, do a Control V, and I want to change the value of x in this. Let's see, I guess I need to go much further over this way. Backspace, and I'm going to put in 0.4. So the value of f at 0.4 is about 0.5106994. Now I also want to know the derivative of f at 0.04. So I'm going to use a difference quotient to estimate the value of the derivative. And I'm just going to use a crude estimate. So I'm going to first write down the numerator, and that's going to consist of f of 4.01 and all of the other stuff remaining as it is, minus, Control V again, f of 0.4. Oh, this should have been over here, 0.41. Let me change that back, or change it to what it should be. 0.41. Okay, and subtract f of 0.4 and divide that difference by a delta x value, which in this case is 0.01, and hit enter. And I mistyped something. Oh, missing a decimal point. So let's recopy that, backspace a little bit, and 0.01. Let's try that again. And this time we get 0.684111369 something. Okay, so let's remember those and go back to see what we can do with them. So first of all, let's just talk about the tangent line approximation again. We saw this in a previous lesson. We can approximate the derivative of f at x by f of x plus h minus f of x over h. And so that means that f of x plus h, for h small at least, and we're talking about f being differentiable obviously, is going to approximately be equal to f of x plus f prime of x times h. This equation can be gotten from this formula up here, just solving it for f of x plus h. Okay, so just to change our notation a little bit, y of x plus h is approximately y of x plus y prime of x times h. And so here's the discrete approximation we can make. Let's let k be some integer. Let's let x of k plus 1 equal x of k plus h. Let y sub k plus 1 be y sub k plus the derivative of y with respect to x at x sub k times h. This formula right here is a discrete version of this formula up here. And we're going to realize that y sub k plus 1 is our approximation for y evaluated at x sub k plus 1. And so we have a number line here, an x-axis, let's say, with points x0, x1, x2, x of 3 through some x sub n. And the length between, the distance between adjacent x sub i's, the length of this little subinterval is h. In a graph, the situation looks as follows. Suppose that here is the function f of x, or y of x, whichever we want to call it. And on this curve, we have a point, x sub k, y sub k. If we find the tangent line to this curve at this point, here it is, and if we move over a distance h horizontally, we get another point on this tangent line, and this has coordinates x sub k plus 1, and I'm just going to call it y sub k plus 1, which is this thing right here, or more accurately, this one down here. So this is a discrete approximation to the y value for this x value on the curve. Notice that this point is actually on the curve, and for a small value of h, this point is still going to be pretty close to the actual solution curve. And that shows us why this solution approximation makes sense. So let's use Euler's method to numerically solve this initial value problem. This is the differential equation that we're looking at in this lesson. We saw that y of 0.4 was about 0.510699. Y prime of 0.4 was about 0.68411,369. Okay, so here's what we'll do. We're going to set it up as a system of first order linear equations. And so to do that, I'm going to let w be y, and I'm going to introduce also a variable z, which is the derivative of y with respect to x. Okay, well in that case, if we look at this equation and differentiate both sides with respect to x, the derivative of w with respect to x is equal to the derivative of y with respect to x, but that derivative of y with respect to x is equal to z. So the derivative of w with respect to x equals z. Also notice that to get a second derivative formula, if we differentiate this one with respect to x, we get the derivative of z with respect to x equals the second derivative of y with respect to x, which is what we have here. So then, what do we substitute in for the second order equation? Well, two first order equations. the derivative of w with respect to x is z, which is what we had right here. And this second one comes from here. If we solve this for y double prime in terms of the other stuff, we get y double prime is 1 over x times y prime plus this stuff times y, or minus this stuff from y. We're basically subtracting these two terms from both sides of the equation. So, but y double prime is the derivative of z with respect to x. That's what we had right here. So the derivative of z with respect to x is equal to 1 over x times y prime, which is z, minus this stuff, which is this, times y, which is w. Okay, so what we're going to do then is to pick a small increment, which I'll call h. I'll let it be greater than 0. The initial value of x is 0.4. The initial value of y is 0.510699. And the initial value of z, which is the derivative of y with respect to x, is 0.68411 approximately. So in a loop, here's what we're going to do. We'll let x sub k plus 1 equal x sub k plus h. Then we'll update our value of y, which is stored in w. W sub k plus 1 is w sub k plus h times the derivative of w with respect to x. But the derivative of w with respect to x is just z sub k. So w sub k plus 1 is w sub k plus h times z sub k. Z sub k plus 1, on the other hand, is z sub k plus h times the derivative of z with respect to x. We recognize this just as a tangent line approximation, and we found out that the derivative of z with respect to x was all of this stuff that's in here. And so this formula just becomes z sub k plus 1 equals z sub k plus h times this stuff. Okay, and then we can write a program to initialize x, w, and z, and then in a loop produce these points. And if we're going to plot x versus y in this, we're going to plot x versus w, because w was y. And so that's what's going to happen in the program that we'll next see. So here is the program using Euler's method that we just saw. When we execute this program, this is the graph that is produced by this plot statement down here, plot x versus w. And we see it starts at 2 here. So y of 0 is equal to 2. Y prime of 0 was minus 1. And if we look at this, the slope here looks like it's probably about minus 1. Okay, so this is the output from this numerical approximation. So now let's compare the two approximate solutions to that initial value problem. We used a partial sum from the power series solution to that initial value problem to generate this graph, and we used Euler's method to generate this graph for the same initial value problem. Power series versus Euler. If you look at these fairly carefully, it's very hard to see any difference between these two curves. They both start at 0, 2, and the graph of these end up here. And notice that the vertical axes are the same, and they end up at about just the same height here, I guess. So visually, at least, they appear the same. It might be interesting to take the difference of these two approximate functions and see how close it is to 0 for all terms, but we're not going to do that right now. So what we want to do now is figure out what the solution, more or less corresponding to y sub 1 of x, is if we want to extend it to the interval from -3 to 0, the negative side of the x-axis. X is between -3 and 0. Okay, so let's see. We have a solution y sub 1 of x that holds at least on 0 to 3, x between 0 and 3, given by a Frobenius series. Can we find a corresponding function, let's call it z sub 1 of x, on -3 to 0 that satisfies the same ordinary differential equation? In other words, we want it to satisfy z double prime minus 1 over x z prime plus 1 plus 8 over 9x squared, this quantity times z equals 0, for all x between -3 and 0. So here's what we'll do. We'll define z of x to be y1 of minus x. Then by the chain rule, z prime of x is the derivative with respect to x of y sub 1 of minus x, this stuff up here. And by the chain rule, that's y sub 1 prime of minus x times the derivative with respect to x of minus x, which is minus y sub 1 prime of minus x. Similarly, using the chain rule again, we can show that z double prime of x is equal to y1 double prime of minus x. And now we'll see what happens when we substitute these things into this equation and get everything in terms of y sub 1. We would like to show, we hope that this is true, the second derivative of z minus 1 over x times z prime plus 1 plus 8 over 9x squared times z equals 0 for all x between -3 and 0. You'll notice that this is the same equation that we had in terms of y earlier, but we know that this holds for all x between 0 and 3. I'd like to show that this one up here holds for all x in -3 to 0. So here's what we'll do. We'll define z of x to be y1 of minus x for x between -3 and 0. Then minus x is going to be between 0 and 3. And so here's what we have using the chain rule from the previous slide. We know that z double prime of x is equal to y 1 double prime of minus x. We also know by the chain rule that z prime of x is equal to minus y1 prime of minus x, and also z of x equals y1 of minus x. Basically, if you start with this one, differentiate using the chain rule, you will get this one. Differentiate again using the chain rule, we get this one over here. So look at this stuff right here. Here it is again. And now we're going to make substitutions to get this in terms of y. Well, z1 double prime is just y1 double prime of minus x. This z prime of x here is equal to minus y1 prime of minus x. And also we'll make a slight algebraic manipulation here. Minus 1 over x is the same as plus 1 over minus x. So that explains how this term corresponds to this one. They're equal. And then for this one over here, x squared is the same thing as minus x quantity squared, so that's easy. And z of x is equal to y of minus x, y sub 1 of minus x. And now we look at this, and we're going to make one more simplification. I have plus this times minus this, and that's equal to minus this fraction times plus this stuff. So basically minus times a plus here gave us a minus here. The other two terms are not changed. But then look at this. In this equation right here, minus x is somewhere between 0 and 3. So here we have y1 double prime evaluated at a number between minus 0 and 3. And the same here, it's evaluated at minus x between 0 and 3, and also over here. And so what that tells us then is by this equation right here, just replacing all the x's with minus x's all the way through, and that minus x is in 0, 3, this stuff has to equal 0. So looking at what we just showed, this stuff here equals this stuff here equals this stuff here, which equals 0. That shows us that z satisfies this equation for all x between minus 3 and 0. So that's nice. We have that y1 satisfies this equation, and when we define z in terms of y1 this way, it also satisfies this equation, but for x on the negative axis. So here are two graphs. Here's a solution to the differential equation on the interval from minus 3 to 0. We called this z of x. We also called it, I think, z sub 1 of x, same thing. And it looks like this. And if you think about what we saw for y1 before, this is just a reflection of y1 through the y-axis. Now, if we put the graph of z of x, which is this part right here, connected with, or in addition, put on the same axes the solution function y1 of x, which is right here, excuse me, we get this graph for a solution, a Frobenius solution to our ordinary differential equation, at least on the interval from minus 3 to 3. So I'll let you answer the following question. Think about it for a while. What about this point right here, which looks like it's 0, 0? Does 0, 0 satisfy the differential equation that we started with in this lesson or not? That should be a pretty easy question to answer. And now for some concluding remarks. There is more to learn about ODEs with singularities and the Frobenius method. We saw one problem, and in our one problem we had two solutions to the indicial equation. R1 was 4/3 and R2 was 2/3. And here's a fact. If the indicial equation has two solutions, R1 being greater than R2, with R1 minus R2 not being an integer, then there are two linearly independent Frobenius series solutions to the ODE. So in our case, the two roots were 4/3 and 2/3. R1 minus R2, 4/3 minus 2/3 equals 2/3. Last time I heard 2/3 is not an integer. So this fact up here tells us that we would indeed find two Frobenius series as solutions to that differential equation. There are other techniques, such as reduction of order of the differential equation, that need to be learned in order to handle other cases not covered in this lesson. So what did we accomplish in this lesson? Well, we found two linearly independent Frobenius series solutions to an ordinary differential equation that had a regular singular point at x equals 0. We called those two solutions y sub 1 of x and y sub 2 of x. We also used Euler's method, tangent line approximation, to find a numerical solution to the same ordinary differential equation by picking initial conditions that corresponded to our y sub 1 of x function, and Euler's method gave us the graph of a solution that looked identical, to the eye at least, to y sub 1 of x. We compared the two, and since they appeared identical, that was good news. That meant we were on the right track, probably didn't make any stupid mathematical errors along the way. We then looked at extending the solution y sub 1 of x to the negative x-axis, and we found a solution to our ordinary differential equation that held for x between -3 and 3. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.